All right, hey gang, Holocaust Museum today, huh? I've never been to one myself. Was in DC, and I guess there's a pretty good one there. Would like to go to that one someday. So I hope that your time there is well spent. Yeah, you learn from the past, so you don't repeat past mistakes. So would love to hear some stories if you guys have some coming back tomorrow. So. What I want to take a look at today is going to be section 5.1, and we're going to get right into it here. So let's take a look here. We've got about 4 theorems that we're going to go over that are not difficult theorems, but I think they will, yeah, I hope they're pretty straightforward for you. So let's take a look here real quick and get through this. So the first theorem is called the perpendicular bisector theorem, okay? Let me go ahead and try to focus that a bit more. There we go. And it starts out like this. If a point lies on the perpendicular bisector of a segment, then what is true? Well, if you take a look here, I'm going to go ahead and show that there's a segment here, okay, or a line that is going to be the perpendicular, so right angle, and it's going to be the bisector of segment AD, okay? So right now, if CD is the perpendicular bisector of AB, then what is true? Well, if I go ahead and find just a random point, doesn't matter where that point's located, above or below that line, it doesn't matter where, and I go ahead and draw this line in here, and draw this line in here, okay? And let's label that maybe point B, okay? Well, what do I know about point B? Well, I do know that these two triangles are going to be congruent, all right, by side angle side or leg leg, okay? So maybe I'll say this: triangle AB. No, I don't want to go into that right there. We'll just note that. And maybe I'll put that down here. Triangle ABC is congruent to triangle DBC by side angle side or leg leg. Okay, just something to think about there. Now, if that's the case, then what would be true? Well, we would then know that AB, and actually I'm going to put that up here, that AB is going to be congruent to BD by, actually I'm not going to put that there, maybe I'll put it down here. AB is congruent to BD by CPCTC. Okay? So the essence of this theorem is this: that any point that lies on this perpendicular bisector that's cutting this segment in half perpendicularly, then it's going to be the same distance from those endpoints, okay? So the conclusion is this: if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay? So if that's the case, let's go down here and look at an example. If that's the case, this line right here lies on the perpendicular bisector of this segment. So what's true then? Well, I don't have to prove the triangle's congruent anymore. We've already done that. We know that these two segments will be the same length. So if I'm going to go ahead and set up the equation to solve for x here, here's what it would be, okay? So in solving for x, subtracting 2x from both sides, adding 7, and then dividing by 2, we get x to be 5, okay? But if we're trying to find QR is going to be, let's see here, 2x plus 3. So 2x plus 3 would give us 18. That is the length of QR, okay? So again, with these type of problems, make sure you finish them up all the way, okay? Now, the next one says this, the converse of that same theorem. If a point is equidistant of the segment, then if it's the same distance from the endpoints of a segment. So if I go ahead and mark this out, just like that, okay? I'm going to go ahead and drop a line down. Now the shortest distance from this point to this line, we've talked already this year, is a perpendicular line. So I'm going to drop it down in a perpendicular manner, okay? So what do I then know is true? I'm going to make this point D. Well, I know that CD is congruent to CD by the reflexive property. And therefore, the triangles here, let's say ADC and BDC, are congruent by hypotenuse leg. Don't forget that one, remember? Okay. If that's the case, then I would know that AD is congruent to BD by CPCTC. Okay? Well, why is that important? Well, basically what happens here is this. If you have a point that is the same distance from the endpoints of a segment, then that point has to lie on the perpendicular bisector. Okay? So if I have a point right here that is the same distance from A as it is from B, then that point must lie on this perpendicular bisector. Okay? So if AC is congruent to BC in the picture there, then let's say CD perpendicularly bisects it would be AB. Okay? Now, the theorem, just to put the theorem down, so if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. It is on the perpendicular bisector of the segment. All right, so with that being said, if I go down here to an example problem, notice that x, y, and wy are the same distance from w and x are both the same distance from y. So what does that mean? Well, that means that this line right here, this line could be anything. It doesn't have to be a perpendicular bisector, but the implications that they're trying to get you to understand is this point must lie on the perpendicular bisector, so the line that they're drawing in is the perpendicular bisector. So when they ask a question like, what's the measure of angle WZY, then we want to tell that it is a 90-degree angle, okay? The other part, how do we figure out what WZ is, this length here? Well, we're going to set up this equation because if it's a bisector, these two lengths have to be the same. And so I'm going to say 3x plus 2 is equal to 4x minus 5. And I'm going to go ahead and solve for x from there. So subtracting 3, I get x. Adding 5, I get 7. And if we're trying to find wx here, then I'm going to go ahead and do wx, which is 3 times 7 plus 2. And that would make 23, which is the length of wx there. Okay? So I really think the nice part about these theorems, folks, is you could probably guess how to solve them without knowing the theorems here. I just want you to know the background information, okay? So the next one is the angle bisector theorem. If a point lies on the angle bisector, then what is true? Well, I'm going to drop a line down. If you notice, this, let's go over here a bit. This point is on the bisector of this angle. Both these angles are the same, okay? So I'm going to drop a line down perpendicular to this side, the shortest distance, and I'm going to drop a line down perpendicular to this side over here, okay? And by doing that, I'm going to make this point C and this point D, okay? Now what I have then done is made congruent triangles here, okay? How do I know? You could say by angle, angle side, or you could say by hypotenuse angle, either way. So let's just make a note of that here, that triangle ABC is congruent to triangle ABD by angle, angle side, or hypotenuse angle, okay? Now from there, if that's the case, we then would know that this length AD is the same length as AC. Again, this is by CPCTC. Okay, so the conclusion that I want you to understand, if BA bisects the angle, then AD D is congruent to AC. Okay, that's the key here. And what the theorem reads is this: if a point lies in the bisector of an angle, then it is equidistant from the sides of the angle. There you go. Okay. So how does this play out? For a lot of you that play baseball, I hope you can visually see the baseball diamond here, okay? Where does third base lie in relation to first and third? Well, it's the same distance, right? So where does I said that wrong. Where does second base lie with respects to first and third? It would be the same distance here. We also know that second base lies on the angle bisector of the first baseline and the third baseline, okay? All right, now, to finish things off, to find QS, these triangles are congruent, so therefore I'm going to mark those two segments congruent there. 4x minus 1 equals 3x plus 2, okay? And if I go ahead and solve for x, I get x equal to 3, so QS is equal to 4 times 3 minus 1. 12 minus 1 is 11. The length of QS is 11, okay? All right, one last theorem to go over here, folks, and here's what it says. If a point in the interior of an angle is equidistant from the sides of the angle, then what is true, okay? So what I've done here, as you can see in the picture, I've went ahead and drawn a point that is on the interior of an angle, and it's the same distance from the sides of the angle. Now again, I drew it the shortest distance to the sides of the angle by making it perpendicular, okay? Now, what we're going to find out here is this. Since AD is congruent to AD, we then would know the triangles here are congruent, triangle ABD and triangle, let's see here, ACD by hypotenuse leg. That's a little harder to see, but there's the hypotenuse and there's the legs, okay? And if that's the case, then angle CDA is congruent to angle BDA by CPCTC. Okay? So the key here is this right here. This is what we're getting at, okay? So then angle CDA is congruent to angle BDA. That's the final conclusion, okay? So what does the converse of the angle bisector theorem read? It says if a point is on the interior of an angle, is equidistant from the sides of the angle, then it is on the bisector of the angle. It is on the bisector of the angle. Okay? So, again, folks, I know that was a fast and furious lesson there, but I hope that you caught everything. And if you have questions, let's come back and talk about it. But like I said, these are pretty straightforward theorems. You could probably just look at the picture and know what the equation is supposed to be. So, hey, I hope you had a great day, and we will see you tomorrow.